Hello everybody, my name is Antonio and today I'm going to present our paper Explicit Regularization in Overparametrized Models via Noise Injection. This is a joint work with Hans, Anand and Francis. There are several techniques that can be used to boost generalization in deep learning. There are classical approaches such as L2 and dropout, but also more modern approaches such as sharpness-aware minimization and adversarial perturbation. One technique that is very dear to us is noise injection. Noise injection can be used for several problems during training, such as avoiding saddle points and boosting generalization. In our paper, Anti-correlated noise injection for improved generalization, we showed that a specific type of noise injection in gradient descent is able to improve test performance by a large amount in simple problems and also works in deep learning. Here are several papers that discuss noise injection. One very popular technique is to inject noise before computing the labels. So you first perturb the labels, then you compute the gradient of the resulting loss function, and that provides some regularization that has also some theory behind it, and this regularization then provably improves test performance. But noise injection can be used also after computing the gradient. So you first compute the gradient of your loss and then you perturb the weights. That basically makes the process like a stochastic differential equation driven by a Brownian motion. And this can be used both for escaping sharp minimizer, but also for escaping saddle points. And these are a few papers again that discuss this topic. The picture that one can have in mind when discussing the relationship between flatness and generalization is this classical picture from this Keskar paper in 2016. So it is clear that the testing function is a perturbation of the training function. We don't have access to the test data, therefore what we expect is a test function to be similar to the training function, but with slight perturbations. And of course, if we converge to flat minimizers, these perturbations in the test function actually will not have a drastic effect, while when considering sharp minimizers, perturbation can have a drastically different effect, and therefore is important, at least many people claim that this is important, to converge to flat minimizers. These are a few other papers that discuss the relationship between flatness and generalization, proving that it works, that it's actually precise for some problems, but also outlining that there are other techniques, other measures that one can use to better characterize the relationship between flatness and generalization. Something like adaptive sharpness or something independent on the parameterization of the network. However, what we observed in our previous paper was that characterization of generalization with flatness actually works pretty well on simpler problems, but also on deep learning tasks. I told before that actually this is not the only option, or this is a bit of a conflicting area of research, because many people don't believe that the relationship between flatness and generalization is precise or can be used in the modern setting. And indeed, there is some evidence on very recent deep networks such as transformers that flatness does not necessarily imply generalization, or actually the other way around. So this relationship deserves much attention and is not solved. We need further research on this topic. However, for the purpose of this paper, we take this relation for granted, and we also show that the relationship between flatness and generalization is true on many simple problems. So we want to converge to flat minima, but how do we find them? Using gradient descent. So what we can do, and what we show works, is to inject noise before computing the gradient. And this works for many problems, but needs adaptation in deep learning, and specifically in deep networks where the width also grows to infinity. Let's go on with some theory. So consider model weights W, and consider a loss function that is a combination of L and phi. Phi is the model, L is the criterion, such as cross entropy or L2. So we perturb the weights with this Gaussian standard vector epsilon, and then we compute the gradient and we update the new weights. So in expectation, we will be actually optimizing the following loss, the loss that is in the gray box. This is the expectation of the perturbed model and the criterion of that. let's have a warm-up and understand a little bit more what's going on. So the loss function joint between the criterion and the model we call f. So when expanding f with a Taylor expansion, and of course this is this is an approximation, you can simplify the term because the Gaussian noise makes it very easy to perform simplifications. When you do the proper simplifications, what you get is that the regularized loss that is equivalent to the loss that is minimized by gradient descent with the noise injection in expectation is going to be the original loss plus a regularization term that is dependent on the trace of the Hessian. That is, if the minimizer is sharp, that is the trace of the Hessian is big, then what we have is that the loss becomes less favorable for stochastic gradient descent. So this is very good, and this analysis is simple and provides a direct link between noise injection and sharpness. However, to have a better idea of what's going on, what we can do is a more careful analysis. So let's start again by the regularized loss, and let's expand the model and the criterion L. So when doing a Taylor expansion on both and inserting one into the other, we have something that is actually a little bit more precise. It's equivalent to the formulation we had before with the composition of L and phi, but it reveals an interesting property of the regularizer. That is the expected loss that we are actually minimizing when considering noise injection in stochastic gradient descent is the original loss, plus a term that is in O of sigma square that is 0 for piecewise linear models. Indeed, you see that you have the second derivative of the model, plus a term that is actually also O of sigma squared, but is non-vanishing. And this term is the leftover sharpness-aware term. And also we have a fourth term that is an error term, which we ignore for the time being, but will be important for the later slides. So again, we have another formulation of the regularized loss, and we know that this is the loss we are actually optimizing implicitly when we use noise injection, and we do noise injection actually inside the gradient, because if we do it outside, everything changes and becomes actually trivial. So here we're using the gradient geometry to actually change the loss landscape. So one setting that we can test what this regularizer term actually means is diagonal neural networks. So consider input x, and multiply the input element wise by this vector u, and then multiply it again by vector v, and then compute the loss at the end. So this parametrization is actually a bit hard to work with, and one equivalent parametrization that is also used in the literature is w plus squared minus w minus square, which we call w1 and w2. And we put a screenshot of the appendix where you can find this equivalence. So again, this is equivalent to linear regression again, of course, because what you can do is call beta the vector w1 scalar product w1 minus w2 scalar product w2. So you actually have that in terms of expressivity, you're not going beyond linear regression. However, this parameterization is very interesting to understand training dynamics. So when considering, in this case, the form of a regularizer, we find that this regularizer is actually very related to the L1 regularization. And this is very interesting because L1 regularization has provable connections to generalization. And we can do the same for linear neural networks, and we have the analysis for ReLU networks and deeper networks in the paper. But for the time being, consider phi of w, w2 times w1 times the input. And if you do this and you expand again and compute the regularization term in our setting, what you get is that the regularization term depends on the nuclear norm of the activations. And that again is very related to generalization, and we know by classical machine learning that this might be a very good idea. So the nice thing about this is that we could, in principle, introduce these regularization terms directly into the loss and avoid noise injection, but noise injection provides a regularization that is actually can be actually performed being agnostic of the model, of the specific model that you use. And it has relationship to flatness. And this is what I showed in the warm-up computation. Also, this relationship to the nuclear norm connects back to a famous conjecture by this paper, Implicit Regularization of Gradient Descent Dynamics in Linear Neural Networks. It connects generalization to nuclear norms. Okay, so, but we have a problem. So this is a very, very nasty problem, and a problem that I hid under the carpet until now for this presentation. Let's consider the perturb model output phi. So phi of w plus noise. So when you do this and you expand the network, what you have is you are going to have some perturb input also into the model, but also this term sigma squared E2 E1 x. So E2 times E1 is the noise in the first layer times the noise in the second layer. And this term is O of sigma squared, so it shouldn't be much of a problem, because then when we take for example, the squared loss into account, this term is O of sigma fourth power. However, when your network is very deep and specifically very wide, that is in this case D1 goes to infinity, this term can be very problematic, and this is basically variance. So this variance term is going to depend on the specific noise that you inject, and is something not desirable. So when considering a regularized loss, we don't want to be highly dependent on the noise that we inject. We want something that is actually much better controlled. So we want to get rid of this term, but this is not very easy. However, we found a trick to do that. So the trick is perturbing only one layer per gradient step. That is, you increase sigma, okay, so say you have 10 layers, then you take sigma that is adapted to the number of layers you have, a new sigma, and if you adapt that and perturb each layer independently, the terms that involve multiplications of E1 and E2, for example, E1 until EL, that is the depth of the network, all become zero, because at least one of them is going to be zero. And this is a nice trick, and it works very well. So let's consider a neural network on some synthetic data. So on the left side, you can see the original loss dynamics, and on the right side, the regularized loss. On the top row, you have a network with one hidden layer and 50 neurons, and in the bottom row, 300 neurons. So from the left side, like the original loss, what you can see is that gradient descent actually optimizes the original loss, while the other methods don't, of course, because the loss is different. However, when you want to consider the regularized loss, gradient descent doesn't converge to regularized loss. Again, you have a different loss function, but gradient descent with layer-wise noise injection is very close to the regularized loss, while if you inject the noise simply in all layers, you get very noisy dynamics. Let's go on with some experiments on deeper networks. So this is a fashion MNIST network, full batch training, real MLP with 2 layers and 5,000 neurons each layer. And you can see that this is full batch training. Again, you have gradient descent, which achieves 79%. And if you tune the value of sigma with layer-wise noise injection or injection of noise in all layers, and again, the sigmas are adapted such that basically you have the same regularization effect, you actually get much better performance considering layer-wise noise injection. And this can be also observed in deeper networks, also taking into account the effect of width. That is, if you have a wider network, the gradient descent plus simple noise injection inside the gradient performs quite badly. But if you inject the noise layer-wise, then the effect boosts test performance. And this, actually, going back to the original problem, can be seen also in the trace of the Hessian. So the trace of the Hessian is actually minimized. Finally, let's consider what happens in a deeper network, such as residual resonant CIFR10. And you can see that, yet again, injecting noise layer-wise can improve test performance and also provide some trace of the Hessian minimization. So we observe that flatness and generalization are indeed linked, but however, for different type of architectures, the picture might be a bit more complex. However, the boost we get for deep networks with something like normalization layers or skip connections is actually quite minor. It is promising, but we hope that further insights or further work can improve this. And we are working actively towards making this method scalable and to make it work with new architectural components such as attention and normalization. For this, I thank you, and I hope to see you at AI Stats at our poster.